All right, well, welcome back, everybody. So last time we wrapped up our discussion on eigenvalues and eigenvectors. We talked a bit about diagonalization. Remember that if we have some matrix A, some square n by n matrix A, we can diagonalize it, factorize it into the following matrix product of V lambda and V inverse, where lambda is the diagonal matrix of eigenvalues and V is the matrix of the right eigenvectors stacked together. And we can also think about this factorization in terms of this sum of outer products of a series of directions defined by VU Hermitian, this outer product, scaled by some set of magnitudes lambda I. So we also showed that if A is Hermitian, if A is complex valued and it is Hermitian, or if A is real valued and it is symmetric, then we actually have a really nice factorization given by a special theorem. Does anyone remember what that theorem was called? It's a very, very important theorem. Does anyone remember what it was called? All right, well, I'll take your word for it. Spectral theorem, right? Spectral, often when you're talking about eigenvalues or frequencies, we'll talk about it as a spectrum. So again, the connection between the frequency domain and the eigendecomposition, you can think of the eigenvalues as representing our spectrum of frequencies associated with linear transformation. And if we have a matrix that is symmetric, we know that it is always diagonalizable. Again, this is the spectral theorem. It's always diagonalizable. The eigenvalues will always be real, and our eigenvectors will be can be put together as a unitary matrix, such that V is equal to V Hermitian is equal to V inverse. Okay, so that's one case we know where it is always diagonalizable. We talked. Okay. We also talked briefly about the case where it isn't diagonalizable. We talked about the Jordan form. So this can happen, and it often does happen with dynamical systems. I'll show you particularly the case where it occurs later in class today. But in that case, we can't diagonalize it. We can't find a full set of linearly independent eigenvectors. So what we can do is we can put the matrix in what's called Jordan form. It'll typically look something like this, where you'll have some set of repeated eigenvalues, and then above these blocks where those repeated eigenvalues occur, you'll have a 1 in the entry above where that repeated eigenvalue is occurring. It turns out, as we'll show today, if you have a matrix that can be put in Jordan form, you can still compute functions of that matrix. Particularly, you can compute the matrix exponential, which we'll be doing today. And we will end up with when we do that, we're still able to compute the matrix exponential analytically, but it'll end up with a little caveat that I'll show you towards class, the end of class today. Okay, we also discussed modal coordinates. So if we have a dynamical system described by the state space equation x dot is equal to ax plus bu, we can diagonalize the system and turn it into a set of uncoupled differential equations. That allows us to, on one hand, analyze the stability of the system easily. It'll allow us later on to do pole placement. So if we're designing feedback controllers to place the poles of the system, it facilitates that. And it also separates the system out into a set of uncoupled differential equations that can be solved independently. And then we can apply our reverse eigendecomposition to, put the system back in its original coordinates and find the solution. Okay, so we talked about this technique. This is called putting the system in what's called modal coordinates. Okay, are there any questions? And then towards the end of the class, we also talked about the singular value decomposition. Unfortunately, I didn't really give this topic the justice. I think it deserves a bit more discussion than I can give you in this class. In fact, when I was in grad school, I took an entire class on the singular value decomposition and its uses. It's so incredibly useful for so many applications. But essentially, for any matrix A, it can be square, non-square, diagonalizable, non-diagonalizable. you can compute a factorization that is similar to the eigendecomposition, where sigma here is your diagonal matrix of your singular values. They're kind of like the frequency components of your linear transformation. And then you have these unitary matrices U and V transpose that kind of represent a generalization of the eigenvectors of the left and right eigenvectors. And I showed you a couple applications where you could use the SVD to kind of extract information about what are the most important components of the system that you're looking at. So we looked at, for instance, principal component analysis. We looked at how we could perform image compression, rank reduction, and so on. Singular value decomposition is very important, particularly if you're trying to kind of characterize what are the most important features of a system or data set. So it provides a really powerful tool for those kind of questions. Unfortunately, I didn't really get much time to talk about it yesterday, but I would advise you to look into it on your own. That's interesting. What just happened there? This is the butterfly effect. Okay. Cool. Okay, are there any questions on topics that we covered last time in class or in the previous week? Any questions on eigendecomposition, diagonalization, etc.? Okay, so today we're going to be covering two major topics. We are going to be covering matrix functions. So how can we apply arbitrary analytic functions to matrices? In particular, we're going to be interested in the matrix exponential. And using that discussion of how we can compute the exponential of a matrix, we're going to show how we can use matrix functions to solve multivariable LTI systems, which we've been talking about for a while. You know, in your homework, you showed how you could formulate LTI systems for multivariable problems. We're finally going to get to the point where we can solve those problems now. All right, cool. So just to motivate the discussion, let's look back. Let's say we have a system of the form, an LTI system of the following form. X dot of t is equal to ax of t plus bu of t. So this is our standard LTI system. Any LTI system that we can think of, we can put in this form. This is our state space form. It turns out that the general solution to this system is the following equation, which is going to look familiar to you. Let's say we want the general solution to this LTI system. It is given by x of t is equal to e to the at times x naught, our initial condition, plus the integral from 0 to t, and you can probably see where this is going, of e to the a t minus tau b u tau d tau. Okay. So the solution to an LTI state space system is essentially the same as for the scalar case, okay, except now x of t is a vector, x naught is a vector, and u of tau is also possibly a vector. So this is the general solution for the continuous time LTI system. There's an analogous version of this equation for discrete time systems. But you may be wondering, how do we do this? How do we raise a matrix? How do we take the exponential of a matrix? So yes, this may be something that you've never conceived before. So, you know, you might think of just applying the exponential element-wise, right? Except you know that if you have a matrix squared, that's not the same as just squaring every entry of the matrix, right? So it's not enough to simply just naively take the element-wise exponential of the matrix. In class today, we're going to talk about how we can apply arbitrary functions to a matrix. So today we are going to look at how to apply arbitrary functions, analytic functions, to a matrix. And in particular, we're going to take a look at the matrix exponential, which is going to give us the solution to our LTI state space system. Okay, so today I'm going to show you how you can apply arbitrary functions. They can be any continuous analytic function. So for instance, we could compute the sign of a matrix. We could compute the sine of A. We could compute the cosine of A. We could compute the log of A, where A is a matrix. And most importantly, for our purposes, we can compute the matrix exponential. So e to the AT is typically what we're interested in, where A is a matrix and T is a scalar. Okay, so great. That's what we're going to be talking about today. First, let's talk a bit about what it means to apply a function to a matrix, because it may not be exactly clear what I mean when I say we're going to apply a function to a matrix. Okay, so the easiest way to understand functions applied to matrices is to think about them in terms of their Taylor expansions. Okay, so let's say, let's talk a bit about what matrix functions mean. Okay, so let's say we have some scalar function P of A. So let's say we're going to let P of A be a, let's say an analytic function of a scalar variable A, of a scalar variable A. We can say that it's, maybe in the real numbers or in the complex numbers. It doesn't really matter. Okay, and let's say we have that for this function, we have, I'll say with a Taylor expansion about a steady point. So let's just say A is equal to A star, and let's just say that it's equal to 0. So there's we have some analytic function of a scalar variable A, and we're taking its Taylor expansion around A equal to 0. So this would be the Maclaurin series for our function P. So we have that P of A from our definition of the Taylor expansion is equal to P naught plus P1A plus P2 A squared plus P3 A cubed, and so on to infinity, where for each of these coefficients, P naught through, actually for P1 through P infinity, we have that Pk is equal to 1 over k factorial times the partial derivative of our scalar function P of A with respect to A, evaluated at A is equal to A star was equal to 0. And this is for k greater than or equal to 1. And P naught is just simply our function P evaluated at A equal to A star, which is equal to 0 in this case. Okay, so this is just the definition of a Taylor expansion of a function. We can take any analytic function, we can represent it as this infinite series in terms of the powers of the scalar at which it's being evaluated. Yeah, this would be essentially the Maclaurin series. We can define a function P of A in this way. So if instead we have A is a square matrix, let's say it's an R n by n, or C n by n, we can define a matrix function in the same way. So we can define a matrix function in the same way. All right, so we have that P of A, this is going to be equal to P naught times I plus P1 times A plus P2 times A squared plus P3 times A cubed, and so on and so on. So in summary, the analytic function of a matrix is defined the same way that a scalar function is defined in terms of its Taylor expansion. So this is how we can define an analytic function for a matrix. So let's go through a couple examples. So we can look at some examples of the scalar equation and then its matrix equivalent. So let's say we're looking at the exponential function. In the scalar case, this would be exponential of some scalar variable x is equal to e to the x. And if you remember, perhaps back from undergraduate differential equations, we can write this as x to the 0th, oh, sorry, that should be equals, not a plus, x to the 0th power over 0 factorial plus x to the first power over 1 factorial plus x squared over 2 factorial, and so on and so on. Okay, so this here just becomes 1, right? Because 0 factorial is 1. This here becomes x because 1 factorial is 1 and x to the first power is just x. So we end up that the Taylor expansion of an exponential function is given by 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Okay, so this is equal to the exponential of x. So for a matrix, it works in much the same way. Like, let's say we want to take the exponential of the matrix A times some scalar t. We can just define this e to the at as being equal to this Taylor series, right? So we have that instead of 1, we'll have I, the identity matrix, plus at plus 1 over 2 factorial a squared t squared plus 1 over 3 factorial a cubed t cubed, and so on. Right, this is how we can define the matrix exponential. It's simply equal to this infinite series given by the Taylor expansion. So this is the definition of the matrix exponential. But we don't need to constrain ourselves to the exponential function. We can also, for instance, look at other functions. So for instance, the sine of a scalar function, we know that this is equal to ends up being 1 minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th power. So for a matrix, if we take the sine of a matrix, it's simply equal to the identity matrix minus 1 over 3 factorial a cubed plus 1 over 5 factorial a to the 5th power, and so on. Right, so we can define arbitrary functions of a matrix like this. As long as it has a Taylor expansion, we can define a function of a matrix in this way. Okay. Are there any questions on the definition of a matrix function before I move on? In brief, you can define a matrix function in terms of its Taylor expansion, or I guess Maclaurin series technically. Any questions? All right, so I want to make one point before I move on, which is that if you have a function of a matrix, derivatives of that function work in the same way. So if you have 4 matrix functions, derivatives work in the same way. So let's go ahead and take our matrix exponential function and let's try to differentiate it. Let's look at the Taylor series, apply the derivative of that function with respect to t and see what happens. So let's look at our matrix exponential. We have that the exponential of some matrix A times some scalar t is equal to the sum from k equals 0 to infinity of 1 over k factorial times a to the kth power plus t to the times t to the kth power. Okay, so this is our definition of the exponential function. You can see that from this previous slide here. Okay, and let's see what happens when we take the derivative of each side with respect to t. Okay, so we're going to see what happens when we take the derivative of the matrix exponential. So the first thing you might notice is that the derivative is a linear operator. So we can move it inside of this sum here. Okay, so this will be equal to the sum from k equals 0 to infinity of 1 over k factorial a to the kth power, and then we can just apply d by dt to the term that depends on t. Okay, what will this expression become? We take the derivative of t to the kth power with respect to t. Yes, this will become k times t to the k minus 1, right? Okay, so let's go ahead and do that. So we end up with the sum from k equals 0 to infinity of 1 over k factorial times a to the k times t to the k minus 1. And I'm just going to move the k over here. Okay, so we took this k from our derivative of t to the k, and I just moved it over to the top of this fraction here. So how is the factorial defined again? I don't remember what is k factorial equal to? Right, so it'll be k times k minus 1 times k minus 2, and so on, all the way until you get to 1, right? So what will this expression here evaluate to? Right, which would be equal to k minus 1 factorial. Very good. So if we carry out that division, we end up with the sum. Actually, I'm going to leave the indices ambiguous for now. So this will be 1 over k minus 1 factorial times a to the k times t to the k minus 1. Now, can you have a factorial of a negative number? Strictly for a factorial, no, you can't have a factorial of a negative number. So instead, what we can do is we can just redefine our index to go from k equals 1 to infinity. All right, so now note that a doesn't depend on the index of our sum, so we can move a out to the front. So we can take a out. We have a times the sum from k equals 1 to infinity of 1 over k minus 1 factorial times a to the k minus 1 times t to the k minus 1. All right. And what do you notice about this expression here? So one thing we can do is the index that we're summing over is kind of arbitrary, right? It doesn't really matter what the index is as long as we are summing from 0 to infinity. So what we can do is we can redefine the index of our sum to be k tilde is equal to k minus 1. So if we redefine k tilde to be k minus 1, we can rewrite this. We have that this is equal to the sum a times the sum from k tilde equals 0 to infinity of 1 over k tilde factorial times a to the k tilde times t to the k tilde. Now, what do you notice about this expression here? What is this equal to? Sorry? I think you said the answer. Right. So it doesn't matter what index we are summing over, right? All that matters is that we're summing this expression from k tilde from 0 to infinity, right? So this expression inside this sum becomes the exponential, the matrix exponential e to the at, right? So what we have is that if we go back to our original equation, we have that d by dt of the matrix exponential is equal to a times the matrix exponential. So in summary, taking the derivative of a matrix function works the exact same way as the scalar case. Remember that if you have a scalar function, d by dt of e to the a t, this will be a times e to the at, right? So taking the derivative of a matrix function works the exact same way as for the scalar case. And for the case of the matrix exponential in particular, the derivative of the matrix exponential is just a times the matrix exponential. It's the same as for the scalar case. So what this shows us is that for the case of an LTI system, if we have some LTI system x dot is equal to ax, actually, let me write this x dot of t is equal to a times x of t. So this is just the homogeneous LTI system. What does that imply about the solution to this system? Right. So it's the exact same as for the scalar case, right? We have that the solution is x of t is equal to e to the at times x naught. Okay, and we can go ahead and show that. So just to show that, let's say we have our expression d by dt of x of t is equal to a times x of t, right? Okay, we can substitute in our matrix exponential. So we have d by dt of e to the at is equal to a times e to the at. Actually, let me e to the at x naught. And as before, we noticed that the derivative works the same way as for the scalar case. So this ends up being a times e to the at x naught is equal to a times e to the at x naught. Okay. So the solution to our LTI system is given by the matrix exponential. And now note, because in a state space system, we can write any higher order system in terms of just a single state space equation with all of the first order derivatives on the left-hand side. That means that this solution procedure works for systems of any order. Okay, so it doesn't matter what order our system is. We could have like a second order system, like the structural system, a third order system. The solution will always be the matrix exponential for the homogeneous case. Okay. All right. Are there any questions on this concept before I move on? All right. So that takes us to our next question, which is, how do we actually compute the matrix exponential? So I showed you that we could write the matrix exponential in terms of what? Right, an infinite series. But that's not super useful if we're trying to actually compute the matrix exponential, right? We can't actually compute an infinite series. So what I'm going to show you is how we can actually go about computing the matrix exponential, and actually how can we go about computing any matrix function. It turns out that if A, and let's say it's in R n by n, could also be in C n by n, if A is diagonalizable, then any matrix function can be represented by a function applied to the eigenvalues of A? All right, and let me just write this out more explicitly here. What do I mean by a function can be represented as a function applied to the eigenvalues? Let me write it out mathematically for you. So this is an important result. Okay, let A be a matrix in Cn by n, let's call it Cn by n. And it's diagonalizable so that we can write A is equal to V lambda V inverse, with lambda equal to our diagonal matrix of eigenvalues. So lambda 1, lambda 2, all the way through lambda n. Okay, so then if we have any arbitrary matrix function, so if we have P of A, or P is just some arbitrary function, this is equal to V times P of lambda times V inverse, where P of lambda is just the function applied to each one of those eigenvalues. Okay, so you'll have P of lambda 1, P of lambda 2, and so on, all the way through P of lambda n. In other words, if we want to compute a function of a matrix, we can diagonalize it if it is diagonalizable, and then just apply the function to each one of those eigenvalues, and then multiply that factorization together to get the resulting matrix function. Okay, so let's go ahead and just show this because it's not too hard to show. Okay, let's show it. So the first thing we need to note is that if we have our matrix A raised to an arbitrary power, then those powers of A are all diagonalized by the same set of eigenvectors. So let me go ahead and show. So we have A to the K is equal to A times A times A. Okay, and this is occurring K times. Now we can note that we can diagonalize each of these A's. So this is equivalent to V lambda V inverse times V lambda V inverse, and so on and so on. V lambda V inverse. And now note that we could, for each of these products here, we can just rearrange the groups. So we'll have V lambda times V inverse V, lambda times V inverse V, and so on, all the way to V inverse V, lambda V inverse. Okay, so what's going to happen to each of these terms here, these V inverse V terms? Okay, it's going to become the identity matrix. So what that means is that our some arbitrary power of our matrix A to the K is equal to V times lambda times lambda, all the way to V inverse, which is equal to V times lambda to the kth power times V inverse. And note that just from the properties of matrix multiplication, if we have a diagonal matrix lambda, what is lambda to the kth power going to look like? Sorry? Yeah, so each of these elements along the diagonal will just be raised to the kth power. So we'll have lambda 1 to the kth power, lambda 2 to the kth power, and so on, all the way to lambda n to the kth power. All right. Okay, so we showed that basically any power of our matrix A is diagonalized by the same set of eigenvectors, with the resulting eigenvalue simply being raised to the kth power. All right. So what we can show now, let's go back to our Taylor expansion for some function of A, our matrix. We know from before that this is equal to P naught times I plus P1 times A plus P2 times A squared, P3 times A cubed, and so on. Okay, so let's go ahead and diagonalize each one of these terms. So for the first term, we'll have P naught times V inverse. For the second term, we'll have P2 times V lambda V inverse. For the third term, we'll have P3 times V lambda. Sorry, I messed up this index here. This should be P1, this should be P2. So P2 times V lambda squared V inverse plus P3 V lambda cubed V inverse, and so on. Okay. And what can we do to simplify this expression? Note that all of these P's are just scalars. So what can we do to simplify this expression? I think I heard it. So we can factor out V and V inverse. So let's go ahead and do that. Note that V is always being pre-multiplied here. V inverse is always being post-multiplied. So we can just take V, put it out front. Then we'll have V P naught plus P1 lambda plus P2 lambda squared, and so on. And on the other side, we'll just have V inverse. Sorry, that should not be A, that should be lambda. Okay, so we can just factor out that V and V inverse. Okay, so let's take a look at this term here and think about what it's going to look like. So we can write this as PO times the identity matrix, just for correctness here. So what is this matrix going to look like here? First of all, what's its structure going to be? Diagonal. And what will the elements along the diagonal be? Yeah, so you'll have, for instance, if you have just an arbitrary entry of this, let's say it's the kth entry, we'll have P naught plus P1 lambda K plus, P2, and so on. Okay, and what is this? Well, not quite. It's the Taylor series of what? It's not necessarily an exponential. So this is just some arbitrary function.
Oh, yeah.
Right, so this is P applied to lambda K, right? This is our function applied to the kth eigenvalue. Okay, so in other words, P of A is equal to V times this diagonal matrix where each element is P applied to the kth eigenvalue times V inverse, which proves our assertion that we can find any matrix function just by applying that function to the eigenvalues of the diagonalized matrix. Okay, so for instance, if we have e to the AT, so I'll just say, for example, if we have e to the AT, this is going to be equal to V times e to the lambda 1t, e to the lambda 2t, and so on, all the way to e to the lambda nt times the inverse. Great. So this is an exact solution to finding a matrix function. Note that this doesn't rely on any approximations like truncating an infinite series. This is the exact solution to finding an arbitrary function of a matrix. And in particular, for the matrix exponential, it's going to be equivalent to just diagonalizing the matrix, taking the exponential of those diagonal eigenvalues, and then computing the product to determine the solution. Okay, so very quickly, before I move on to our next topic, I just want to show you what it might look like if you have a matrix that's not diagonalizable and how that changes the result. So I'm not going to go through the whole theory of what matrix functions of non-diagonalizable matrices will look like in the general case, but I just want to show you for the case of a matrix exponential. So let's say for a non-diagonalizable matrix, let's say that we have A is equal to, let's call it lambda 1, 0, lambda. So note that this matrix here, this is in Jordan form. Well, actually, let me just call this J. Okay, so this has the characteristic form of a matrix in Jordan form. So if you have a matrix like this, when you compute the exponential, so e to the jt, you will get, instead of having elements only along the diagonal, you'll end up with a matrix that looks like this: e to the lambda t, 0, t e to the lambda t, and e to the lambda t. So essentially, in this case, in the elements where you have these ones above the diagonal, you will end up with expressions that look like t times e to the lambda t. So what do you think this corresponds to in the case of dynamical systems when we have a system that ends up not being diagonalizable and it can only be expressed in Jordan form? So thinking back to the first half of the course, what case do you think this might correspond to? The case of repeated roots, right? We found that for the case of repeated roots, when we tried to compute the solution, we would often end up with these terms like t times e to the lambda t. When you're computing the solution in state space form like that, it comes out in this form where you'll end up with these terms that are caused by the Jordan form because we couldn't diagonalize the matrix. Okay, so I just wanted to show you what that case looks like. There's more information in the notes about how this generalizes to higher order systems or for different kinds of functions, what those look like when they're applied to matrices in Jordan form, but I don't think it's going to be too important to get into that in class today. So just consult those notes if you are curious, okay? Great. Are there any questions on matrix functions, the matrix exponential, Jordan form, or anything else? Any questions? So who knew before today that you could compute the function of a matrix? Anybody? Yeah, maybe, no. Okay, cool. Yeah, so a couple of you. So yes, I find this subject pretty fascinating. So it's always fun to review it. Okay, so let's kind of take a more practical look now. So we looked at the theory of how we could compute matrix functions and specifically how we could compute the matrix exponential. Let's use this knowledge for solving linear systems of ordinary differential equations. I'll just say solving LTI systems. Okay, so first let's look at the continuous time case. I just want to give you the full solution for each case. So in continuous time, we have systems of the form x dot of t is equal to ax of t plus bu of t. These are all vectors. And we have that if we have some observation equation, we have that y of t is equal to cx of t plus du of t. So the general solution, which I gave you before, we have that x of t is equal to the matrix exponential e to the at times x naught, our initial condition, plus the integral from 0 to t of e to the a t minus tau b tau u tau. Oh, sorry. This is LTI, so b does not depend on time. So b u tau b tau. Right. And if we want to get y of t, all we have to do is pre-multiply by c and add dut, right? So this is the general solution for a continuous time system. Just for completeness, I want to also give you the solution for the discrete time system. So let's say we have a system of the form x at time index k plus 1 is equal to x at time k. Okay, a times x at time k plus b times u at time k. And we have that our output y at time k is equal to cx at time k plus b times u at time k. Sorry, that's wrong. Should be d. All right, so the general solution for a discrete time system of this form is analogous to the scalar case. So it'll be that x at time index k is equal to a to the kth power times our initial condition x naught plus the sum from L equals 0 to k minus 1 of a to the k minus L minus 1 times b u L. And if we want the output, we just pre-multiply by c and add duk. So those are the general solutions for the continuous time and discrete time case. What I'm going to do now is I'm going to go through a couple of different methods for actually solving LTI systems. You will be using this on the final homework, which I will assign fairly shortly. It'll be a shorter homework so that you have time to work on your projects, but you will need this knowledge for that homework. So what I'm going to do is I'm going to go through 3 techniques for solving LTI systems. And we're really just going to be looking at the homogeneous case because what we're going to be doing is showing different techniques for computing the matrix exponential in particular, because that's the tricky part. You can recover the particular solution by convolving that matrix exponential with your input. So let's cover 3 different ways of solving this by hand. The first way is through the eigendecomposition, as I alluded to before. The second way is through the Laplace transform. And the third way is through something called the Cayley-Hamilton theorem, which is also a really fascinating theorem, which unfortunately I don't have time to go through in this class, but it's a really fascinating theorem, and I'll give you a little bit of a preview about what Cayley-Hamilton is about. Okay, so there are 3 techniques I'm going to show you. Note that if you're actually computing the matrix exponential numerically, these techniques typically won't be used because they're not numerically efficient. So I think I posted a supplementary material on how it's actually computed on a computer. I think Tade approximations are usually the techniques that's used for computing the matrix exponential. But I'm going to go through this process just to kind of give you some practice and intuition for solving LTI systems. All right, so let's go through each of these different techniques. And for the first example, let's take a look at using the eigendecomposition. We're going to use our structural system again. So we have our structural system with the same parameters as before. So we have that the let me just write that this example is using the eigen decomposition. So that we have that our state space system for the homogeneous case is of the form x dot, x double dot is equal to 0, 1, -2, -3. Those are the parameters that we used last time, times the vector x dot. So to compute the matrix exponential via the eigen decomposition, what we're going to do is we're going to say that e to the at is equal to v times e to the lambda t times v inverse, right? So let's go ahead and just recompute the eigenvalues again, just for practice here. So let's say that we have, how do we compute the eigenvalues again? Yeah, so we can do 0 is equal to the determinant of lambda I minus a. So this is going to be equal to determinant of lambda -1, 2, lambda plus 3. We carry out the determinant. What will our equation end up as? How do you do the determinant again? Lambda times lambda plus 3 minus -1 times 2. That'll give us lambda squared plus 3 lambda plus 2 is equal to 0. And if we factorize this, we know that the roots are equal to, let's see, if we factorize this, we get lambda plus 2, lambda plus 1, right? So our roots are -1, -2, very good. Okay, so we know that our diagonal matrix lambda is going to be -1, 0, 0, -2. Okay. All right. So we also know from a previous class session, we computed the eigenvectors. So we know that v is equal to 1/√2, -1/√2 in the first column, -1/√5 in the second column, 2/√5 in the second column. And we know that v inverse is equal to 2√2 in the first column, √5 in the first column, √2 in the second column, √5 in the second column. All right, so if we want to compute the matrix exponential, all we have to do is multiply v times e to the lambda t times v inverse. So let's go ahead and do that. We have e to the at. Let's just write out v again. I won't say it out loud, but I will just write it. Okay, and then we have that this v is being multiplied by e to the lambda t. So what are the entries of e to the lambda t going to be? What will the first entry be? So we have that lambda is equal to -1 and -2 along the diagonal. So what will e to the lambda t be? Okay, can I get one e to the -t, right? 0, 0, and then this one will be e to the -2t. Okay. And then we have that this v inverse is the same as before, so I'll just write it down. I won't say it. All right, so all we have to do now is just multiply these matrices together. And I'm not going to do it because it's really tedious, but what we'll end up with if we multiply these matrices together is we will get 2 times e to the -t minus e to the -2t. I'll just write out these lines to separate it here. So in the first row, we'll have 2e to the negative t minus e to the negative 2t. In the second row, second column of the first row, we'll have e to the negative t minus e to the negative 2t. Here we'll have negative 2e to the negative t plus 2e to the negative 2t. And the final element will have negative e to the negative t plus 2e to the negative 2t. Okay, that's just what you get when you multiply out this big matrix product. And this is the matrix exponential. So if we want the solution to that LTI homogeneous system, we can just say that x of t is equal to this expression times x at time 0, x dot at time 0. So let me write this out explicitly here. We have that x, x at time 0 is equal to this expression here. All right, sorry, that should be x at time t. All right, so that's the first way that you can compute the matrix exponential. Let me show you the Laplace transform, and then if I have time, I'm going to show you Cayley-Hamilton, which is just a really interesting subject in its own right. So let's show how we can compute the matrix exponential using the Laplace transform. So first, note that if we have a system of the form x dot of t is equal to a x of t, note that the Laplace transform is a linear operator. So we can just take the Laplace transform and apply it to this matrix equation as well. And we kind of did this in the previous class or 2 classes ago. So what will this left-hand side become if we take the Laplace transform? Yeah, so we'll have x of s minus x at time 0, right? And then on the right-hand side, we'll just have a times x of s, right? All right, so let's simplify this a little bit. Let's go ahead and just move things around. So I'm going to move this x at time 0 over to the right-hand side, and I'm going to take this x of s and put it together with this x of s. So we'll end up with s times x of s minus a x of s is equal to x at time 0. And we can go ahead and we can just factor out our x of s. So we'll have x of s times quantity si minus a is equal to x at time 0. And how can we get an expression for our solution x in the frequency domain? All right. Take the inverse. So let's take x of s is equal to si minus a inverse times x at time 0. And then all we have to do is, what do you think we can do to get the solution in the time domain? Inverse Laplace transform. So what we have is that x at time t is equal to the inverse Laplace transform of si minus a inverse times x at time 0. What does that imply about this here? What is this expression equal to? What is this? We have that x at time t is equal to something times x naught. Sorry? Well, the transfer function would be in the frequency domain, right? What was the homogeneous solution again to an LTI system? Right, this is the matrix exponential. Right, so this is the Laplace transform. Unlike the other methods that I'm going to show you, this can only be used to compute the matrix exponential. It can't be used to compute other functions of A. But for this, essentially, from this derivation, we can see that taking the inverse Laplace transform of SI minus A inverse is equivalent to computing the matrix exponential of AT.
Like the Laplace transforms the same.
Yes, so it's a linear operator, so it's just applied element-wise. Yep. Okay, so let's go through an example. And just to kind of speed things along, I'm going to use a simpler system. So we're going to be looking at a harmonic oscillator. This will make it a little bit easier to compute. So our harmonic oscillator will be given by a state space system of the form x1 dot x2 dot is equal to 0, 1, -1, 0 times x1, x2. All right, so we know that our solution in the frequency domain is given by x of s is equal to si minus a inverse times x at time 0. So let's go ahead and compute this term. This is called the resolvent, si minus a inverse. Okay, so first let's look at si minus a. This is equal to, what'll this be? What'll the first element be? S. Second element? -1. Third element? 1, and this will be S, right? Okay, so that's Si minus A. So to compute the inverse, what do we need to do first? Right, we need to compute the determinant, right? So let's compute the determinant of Si minus A. So this is going to be equal to S squared plus 1, right? Okay, so the inverse of Si minus A will be equal to 1 over the determinant. So that's 1 over S squared plus 1. And then how do we compute the determinant of a 2 by 2, inverse of a 2 by 2 matrix? Okay, so we just switch these diagonal elements and then we multiply the anti-diagonal by -1. So it'll be S in the diagonal and then 1, -1 in the anti-diagonal. So what this will become is S over S squared plus 1, 1 over S squared plus 1, -1 over S squared plus 1, S over S squared plus 1. Okay, so we have, this is our expression for Si minus A inverse. What do we need to do now to compute the solution in the time domain? Take the inverse Laplace transform. So let's go ahead and do that. So let's go ahead and take a look at our table of Laplace transforms. Let me just pull it up real quick. All right, and let's see what entries these elements correspond to. So we have S over S squared plus 1, and we have 1 over S squared plus 1. So if we go here, what does that correspond to here? These two, right? So we'll end up with where S is in the numerator, we'll have cosine of t. And with 1 in the numerator, we'll have sine. So our expression for, if we take the inverse Laplace transform of Si minus A inverse is going to be the inverse Laplace transform of, what was that expression we had? So this will be, let me just write it out here just to avoid rewriting it. This will be cosine of t. This will be sine of t. This will be negative sine of t. And this will be cosine of t. Okay, so we take the inverse Laplace transform. What we'll end up with is that the matrix exponential e to the at is equal to cosine of t, sine of t, negative sine of t, cosine of t. Does this look familiar? Okay, what is this? Sorry? Is there a special name for this matrix? A rotation matrix. So we have the solution to the dynamical system that I gave you, this harmonic oscillator. The time dynamics are given by a rotation matrix. So as t increases, your point wherever you started is going to essentially just rotate around the origin indefinitely. Okay. So for this problem, the Laplace transform was easier to compute than the eigen decomposition. There's just a lot fewer computations in this case. Okay, I don't think I'm going to have time to show you the Cayley-Hamilton approach. I can just give you a very quick overview of Cayley-Hamilton, just because I think it's a very interesting fact. Okay, so what the Cayley-Hamilton theorem implies is that every matrix satisfies its own characteristic equation. So the Cayley-Hamilton theorem states that the characteristic equation, every matrix satisfies its own characteristic equation. So let's say we have A is equal to 0, 1, -2, -3. Okay, we know that the characteristic equation is lambda squared plus 3 lambda plus 2 is equal to 0. This implies that a squared plus 3a plus 2 is equal to 0. And we can verify this. If we have a squared, this comes out to -2, -3, 6, 7. A is equal to 0, 1, -2, -3, and then I is 1, 0, 0, 1. Okay, so if we add up a squared plus 3 times a plus 2 times I, what you'll find that if you add this up, you'll get that this is equal to the 0 matrix. So every matrix satisfies its own characteristic equation. This provides a way of computing any matrix function. Essentially, if you follow this fact to its conclusion, you'll find that any matrix function can be written. Let's say A is in C 2 by 2. Any matrix function can be written as a polynomial of A up to the power of n-1. So for the case of a 2 by 2 matrix, this would be alpha 1 times A plus alpha naught times I. For A in C 3 by 3, any matrix function can be written as A2 times A squared plus alpha 1 times A plus alpha naught times I. And in some cases, this provides a really easy way of computing matrix functions that's actually used in some numerical solvers. Unfortunately, I don't have time to cover it today, so I think we are just about out of time. So with that, I'm going to end today's lecture. Next week, we're going to start talking about, we're going to get more into controls, and we're going to introduce the idea of estimators or observers. So next week is going to be really important. We're going to start moving back into controls, but for the state space systems that we've been looking at since the second half of the course. And I'm going to show you how we can also, in addition to controlling those systems, how we can actually design what are called observers to observe the internal states of the system if we only have access to information about a subset of those states. Okay, so with that, I will let you go. Have a great weekend, and I will see you next week.